Yes, thank you. So my name's Avery, and I'm excited to be presenting our work SpEQ. So that's how you say it. You say SpEQ. And yes, so this is a joint work between Toronto and folks at Microsoft Research. And because this is a bit of a sparse-heavy talk, I just want to first make sure we're all on the same page about sparsity. So on the upper left-hand corner, there's some C source code that's implementing multiplication between a dense matrix and a dense vector. And this is a picture just to give you an intuition of what's going on. And in a lot of applications, most of these entries in the matrix might be 0, and that's what you'd call a sparse matrix. So because we're doing like just additions and multiplications, most of the time, the zeros aren't going to affect the computation at all. So it'd be much more efficient for space and for computation if we just toss those zeros away and only store the non-zeros. So one way to do that is go row by row and collect all of the non-zero elements and smush them together in their own matrix. There's many ways to compress these matrices, and they're all called storage formats. So this is an example storage format that has an additional array to tell us like where each row starts and begins, and a third one to also tell us what are the column index of each array. And the details are not important. The important thing is that now it has a big effect on how the source how the source code implements this multiplication, because now it's using these sparse structures that are extremely difficult for a general purpose compiler to optimize if it doesn't know anything about what the code is doing. And the important detail is that these kind of sparse codes are hand-implemented and handwritten in a lot of important programs, in particular like legacy programs. And to go through those code bases and manually rewrite them to something more modern is very tedious and very error-prone. So what we'd like to do, our goal is to take these kind of general codes as input, so we don't assume anything about these codes, and be able to automatically translate them into like a high-performance library or a DSL. So in this case, we're offloading the computation of the sparse matrix vector multiply onto GPU by making some cuSPARSE calls. And importantly, to ensure the correctness of the translation, we also have to assert some preconditions at runtime. And I'll tell more detail about these later in the talk. But first, I just want to give an overview of the total end-to-end pipeline. So SpEQ operates on LLVM IR, and we do some analysis statically to try to detect what storage formats are used inside of the code. And if we do detect sparsity, then we have a pathway to make sure that our guesses were correct. But even though SpEQ is designed to target sparse codes, like to handle sparse codes, there's another path through the pipeline, which is if there isn't any sparsity detected, we can still handle any dense codes. And after some magic in the module that I will explain later in the slide, then we can perform this translation, and that enables very high speedups, which should not be surprising because, as I said before, these are high-performance libraries that are specifically designed for this purpose. So that itself should not be surprising, but here I just want to illustrate what's possible once you step out of trying to force the general purpose compiler to do something and shift it onto a special purpose application. Okay, so now I'll go step by step through the pipeline. And in the first stage, we take the LLVM IR, and we want to analyze it to try and detect all of the sparse structures that might exist inside of the program. And even though this is LLVM IR, I'm going to write it as source code so we don't all have to try to parse LLVM IR. And the first step is we generate a graph that represents the relationships between variables in the program where they're defined and where they're used. So the way to read this graph is there's some j in the program that ranges over 0 to m, and the arrow is used to indicate that j is used in this expression, rho j plus 1, and that expression itself defines some new variable k and so on. So this is the way to interpret this graph. And the crucial insight is that we can generate like this concrete graph from the input code, but at the same time, any code using a particular sparse structure, it should contain a graph that's characteristic of that format. So in this case, we know, for example, any code that's using this particular compressed sparse row format, it should have a graph that looks like this. We don't care exactly what v1 is or v2 or so on. Those are kind of placeholder variables. We just know that this general structure should be found in a code that uses CSR. So if we can construct a correspondence between the two graphs, then that gives us a good indication that this structure probably is being used in the program. But of course, that is just a guess. So there's many things that could go wrong, and the two main issues that pose to correctness is firstly that the input program contains all of the right structures, like it contains all of the right relationships between variables to make it look like it's using a certain sparse structure, but at runtime, the input data is doing something different. So this picture is showing an example of something that looks like a sparse structure, but actually the input data inside does not represent a sparse matrix anymore. So the source code will look exactly the same as another source code doing a sparse matrix vector multiply, but the semantics are totally different. So to blindly do a translation, in this case, is actually a bug. It's not correct. So we have to have a way to make sure this doesn't happen. And the second case is that maybe there are some structures that SpEQ doesn't know about or that it missed. So we have to make sure that we actually caught all of the behavior of the sparse structure. Okay. So the way that's done is through an equivalence check. And it's a little bit complicated, so I'll give a very high-level overview here, and there's like all the details about it in the paper. But the main intuition is that we start with some input code, and we made some guesses about what sparsity is inside of the code. And based off that guess, we should be able to undo the sparsity. We should be able to like symbolically construct reconstruct a dense version from the sparse version. And if we made all the right guesses, then we should be able to prove that these two program versions are the same program. Just one is sparse and one is dense. So that gives us a certainty that we caught all of the sparse structures, and it also gives us the preconditions we need at runtime to check to make sure like the input data is actually representing a sparse matrix. And the way this equivalence check is done is by constructing a joint transition system. So I'll show an example right now. On the left-hand side, I'm showing two iterations of computing a dot product between the first row of the matrix and the input vector. There's two elements, 1 and 1, multiplying by two elements, P2 and P3. And there are two possible cases that can happen in this joint transition system. So this is showing the first case where both program versions are operating on the same non-zeros at the same time. So that's shown by these 4 different states. On the left-hand side, there's the first state. Then it takes one step. It multiplies 1 times P3 and accumulates back to the result. So that gives you the successor state. And these both systems are related, shown by the red dashed line. In other words, they are equivalent under our notion of equivalence. And that's easy to just like eyeball because 1 times P2 plus 1 times P3 is the same both sides. Okay, so that's one possibility. But if you look at the format-free code, we have 1, 1, and then now we have a 0 next. But we have no zeros in the input code. So this is the second possibility that can happen, is that now the dense version of the code, the format-free version, takes a step. In other words, it computes on the 0 element, but the input code does not store the 0 element. It skips it. So now we have to relate this extra state, 1 times P2 plus 1 times P3 plus 0 times P4, to this other state in the input version. So again, this is like easy to eyeball since 0 times anything is 0, and it should be the same. And that equivalence relation is shown, again, with the red dashed line. And in by simulation notions, this is stuttering by simulation relation. Okay. So if the equivalence check succeeds, then we know all of the sparse structures that are occurring in the program. But that doesn't tell us anything about what the program is doing. We don't know anything about the computation. We just know how the data is stored. So we still need to give a name to this computation. And it now doesn't have any sparse structures, which makes it a bit easier. And the way this is done is we have a database of reference implementations that are just written in a straightforward way. Like, for example, the GEMV, the general matrix vector multiplication reference implementation is 2 for loops of C code, and that's it. We have these database of reference implementations, and we want to prove which versions of the reference implementation are equivalent to the input code. So what we do that by generating a bunch of rewrite rules, like one rewrite rule for each reference implementation. You give us a reference implementation in some source code that can be compiled to LLVM IR, and we can automatically generate a rewrite rule where the left-hand side is the function body of the reference implementation, where the arguments are replaced with placeholder variables that can match any term. And the right-hand side is just basically a semantic label. It's just saying, OK, this big bundle of terms can actually just be called this other thing, and we know the semantics of this thing. Okay, so this is a way to just name all of the different segments of the input program. And in addition, we also have some generic rewrite rules on arithmetic, and also some loop transformations. So then the next step is we take the format-free code where we pulled out all of the sparsity, and we represent it as a term in an E-graph. And this is basically represented as where loops are represented as folds, functional folds. And the folds will have lambdas inside to capture the loop body. And it's all defined recursively so that everything will be like a fold or a captured lambda. Okay. So now we have our term in an E-graph. And this term is able to E-match successfully on the rewrite rule that we generated from the reference implementation. And what that allows is the term and the GEMV function symbol to be placed in the same equivalence class. They are proven to be congruent, which means that we know that they're equivalent. So now we've been able to assign a name to the computation that the input code is doing. We know that it's a GEMV, and we know the meaning behind its different parameters, like y, beta, alpha, and so on. So then the final step is we have a name for the computation. It's doing a matrix vector multiply. We know the storage formats and what variables they're operating on. And so it's basically a lookup table, like GEMV plus CSR. You can just look up the library and say, OK, that's going to be SPMV with CSR, and so on. So the translation step is very straightforward. We just look to see what semantics there are and what formats there are and what library calls are available to us. And we evaluated SpEQ across 10 different benchmarks. So some of these are SPMV, Some are gem, some are histogram and reduction. So it's a mixture of sparse and dense codes. And the takeaway here is that the cost of the runtime check is quite low. And the benefit from offloading to optimized implementations is quite significant. Additionally, we compared against other tools that try to match semantics, and we were the one that was able to do it correctly and over the most number of cases. And finally, even though the whole tool is basically a Python implementation, we're mostly on par with LLVM's O3 pipeline. So the latency here, compared to like lots of other equivalence checking tools, is quite low. So yeah, this is SpEQ. The main idea here is to be able to identify, easily identify segments of input code that you care about, map them to nice, efficient implementations, and we have support for sparsity built in. The artifacts are available online, and there's a README about how to add your own reference implementations for code you care about, how to add your own backends. So please feel free to download it and try it out and let me know. And yeah, that's everything I wanted to say. So thank you.
Thank you. We have time for 1 or 2 questions, if anyone would like to head up to the mic.
Yeah, there was one claim on a particular slide where you said that there are 2 problems that are solved by the equivalence checking. And the latter of those 2 problems was missing a format. And I just didn't get that claim because you've got some library of formats, and you've got a false negative if you just don't recognize a given format. In fact, we're already down the branch of the flowchart that said, yes, we recognize the format. So if we fail to miss a format, how is this correctness issue handled helped by the stuttering by simulation?
Okay, sure, good question. So basically, what would happen is when we tried to construct the format-free code, there would still be some sparse, potentially sparse, or not even sparse, but just certain data structures that we can't reason about. We'd fail to construct a strong enough relation between the 2 systems, and the by simulation would fail. Yeah.
Thanks.
Yep. It seemed in when you encoded your programs into egglog, you used binders in your language?
Here, yes.
Yeah. I guess it's kind of a suggestive question. How did you not run into problems with this?
Yes, so I've talked to the egglog people a lot about this because, yeah, this is a well-known problem. The important distinction is that we do not implement a lambda calculus in the egraph. We don't. The lambda is just used for capturing term names, and that's it. Yeah, so we never do any manipulations on the binders.
Oh, okay.
Yeah.
Well, thanks.
Maybe when while our next speaker is setting up, we could have one more question, if anyone has one. I've got a very quick question, actually. So the very early part of your pipeline was basically detecting the sparseness of patterns, and you said it sometimes goes wrong. Mm-hmm. Is it useful to make human beings tell you what pattern they think their code is using?
Yeah, so you can also add your own graphs. Basically, we have the ability to, like, you can have a callback function that gets triggered in the LLVM static analysis, where you can do your own search through the IR. But that's, you know, if you're familiar with LLVM, it's a bit tricky to do. Yeah.
Got it. Okay. Thank you very much. Okay. Let's thank our speaker again.
Thanks.